Okay, um, first I usually start out and on normal lectures and make sure there's not any questions from the previous lecture, anything going on. Nothing much happened. I guess clarify today. I think for those who have the Tuesday lab period, will be the first true lab. But again, just to emphasize, the labs are flipped. So the lab assignment has been posted as a lecture ahead of time, which you can watch, you can complete. You don't have to come into lab, but you can kind of use the labs as extended student support hours or office hours that the TA will be there. So the TA will be there in M111 today and on Thursday at the normal time. If you know find out if you're a Tuesday lab section person and you don't actually start working on things till Wednesday and you find that you actually do have some questions, then as long as there's room in the Thursday section, which there usually will be, then it's fine to go Thursday or vice versa. So I'm okay with the kind of impromptu swapping if that works for you. So feel free to do that. Of course, if there's a section, while you can still change classes, if there's a section that works better for you, then behind the scenes, it's better to actually formally switch into that. But once the semester is off and running, then I'm fine, basically treating those as extended student support hours for the TA. So, that kind of summarizing the announcements we've got here, get out here. So this ICA A2, so if you haven't done the Unit 0 assignments, please do those because that will unlock the rest of the course. Then remember these ICAs, I think there's about 10 of them, and I think we drop like 5. So there's a high number that you end up dropping. But this first one, which is due before Thursday, so it's due basically Wednesday night, is very short, and I wouldn't recommend taking it as one of your drops. So give the ICAs a shot and go ahead and try this one. Then lab one, this is basically a paper-based lab. So this will be a lab that will be good practice for the first homework, which has been released. So it's a lab that helps you go into the kind of high-level intellectual part of modeling. How do I come up with the entities, as we'll define, that move around in a model before I go through the process of actually building a computational model? And so lab one gives you exercise with that. So does this first homework B1. So other things are also available. So there's the next ICA. All the ICAs basically are available. But all the labs are available. The first and second homework are available. So all those are online. This homework B1, the way you interpret that is by the time we get through lecture B1, you technically have all of the information you need to complete that homework. So if you don't want to start it now, you don't have to start it now. If you want to look ahead and start working on it, that's fine. But then it's technically sort of assigned at lecture B1, which will be Tuesday of next week. So that's kind of how the timing of these things work. So any questions about the layout so far? All right, great. So today, introduction to modeling. Thursday, introduction to simulation modeling. So before we can get to modeling, you have to think about what do we need models for? And that brings us back to a more fundamental question of what is industrial engineering? So I'm just going to have you think about that for a second, and then I'm going to have to ask you some questions about some related questions that are behind all of this. But normally when I ask people what is industrial engineering, a lot of you are third year or fourth year students in industrial engineering, but I think that even at that level in your careers, it can be difficult to figure out exactly what is industrial engineering. It seems like the other engineerings are so much more clearly defined than what industrial engineering is. Usually when I ask this question, I'll get people say things about, well, it's about optimizing existing processes. It's more about economics. It's more about people. A wide variety of things come up. And so that makes us wonder, let's think more fundamentally about, well, what about just science and engineering in general? So before worrying about IE, let's just think about this distinction. So what do people think here? Does anybody have an answer to what is the difference between science and engineering? Any thoughts? There's no real wrong answers here. Yeah, go ahead. What do you mean by the scientific method?
So like testing
So that's what scientists would do? Okay, go ahead. Building versus creating. So your science, you're creating. What are you creating in science? Okay, discovery. So discovery versus building. Yep. So knowledge versus application. So that's maybe a little bit closer to that discovery versus building. Anybody else and want to add to that? And as you again, as you're answering these questions, then think about what does that mean to you as an industrial engineering, or industrial engineer. So if there is this distinction between discoverers and builders, between knowledge and application, then if you're the engineer, where does your discovery come from? Who's doing that for you? So think about that. So that gets us back to, this is a Merriam-Webster definition of science, such knowledge or such a system of knowledge concerned with the physical world and its phenomena. So going along with this discovery idea, a scientist grows the body of knowledge about the natural world by making inferences. This is a scientific method, making inferences from data gathered in experiments. So a scientist says, that's an interesting phenomenon. What's going on there? I ask a causal question. Why is that happening? How does that work? And then I pose hypotheses. I think the heat is doing this. I think the sun is doing this. I think there are certain chemical reactions going on. Or I think that chemicals react in a way that hasn't been tested, but seems to be consistent with this observed phenomena. So I'm going to set up an experiment to test all those possible explanations. And after I test all of them, some of them I'm going to throw out because they're not consistent with my experiment. The other ones I'm going to put in a textbook because they are consistent with lots of experiments. And that's how we grow knowledge. Now, engineering, going back to this application, this is a Merriam-Webster definition. Application of science and math by which the properties of matter and the sources of energy in nature are made useful to people. Useful to people, I think, is an interesting side there. So it's not entirely, according to Merriam-Webster, about an application. It's about an application applied to be the utility of people. So there are scientists that have to do something that looks like engineering in developing their lab experiments. They might say, you might see capstone advertisements for people, needing work on campus where they say, I need somebody to build an apparatus for me. Now that apparatus only has to live for a week. It has to live for the length of the experiment and then it can die off. But we know as engineers that when we design things in the real world, we often have to think about much longer durations. And we might even have to program them to die after a particular amount of time. So the long durations is the utility to a consumer. The dying after a particular amount of time is the utility to the producer. But either way, we are designing these things not just to make use of science and math to build things, but we're building things that have some utility, some often economic utility. That is often what we view as in engineering. So an engineer consumes scientific knowledge, uses the knowledge about the natural world to construct things that are useful in terms of function, accessibility, longevity to people. That's sort of what we view, roughly speaking, as engineering. So, okay, so that sets up a relationship between the scientists and the engineers. So if we think about chemical engineering, so chemical engineering, chemical engineering, the knowledge comes from the chemists and the chemical engineers do stuff. So, the chemists are, they're doing the lab stuff. They're figuring out how these things work. This thing mixes with this thing and this thing happens. The character has all these properties. They give us, potentially there's more physics, periodic tables, etc. All of that stuff is interesting. It tells us about how the world works. But then the chemical engineer takes that and says, that's a really cool property. If I could just figure out how to scale that up, I could turn that into soap or toothpaste or a recycling process. These are all things that are useful to people that incorporate these properties that the scientist has found. Great. Similar with electrical engineering. So electrical physicists are over here. They're, building Maxwell's laws, validating Maxwell's laws, etc. From there, we look at those things, and the engineer takes, the science of how lightning works and somehow turns that into a game controller or a microprocessor or a light bulb. These are things which are clearly not from the natural world. And yet they are built upon the principles of the natural world to do things that you would not expect the natural world to just come up with on their own. And so, but they're definitely related. There's a consumer and a producer. They're doing very different things, but you can't really untie them. Now, industrial engineering. So then it really suggests a question of what's the left-hand side of this diagram? Who are the scientists that are feeding the industrial engineers the knowledge? I think that's a hard question. I mean, if you start drilling down into it, you think about, well, when I think about if I go into a factory and there's a mixture of people and machines, and I'm trying to optimize how well things are working, there are human factors involved. It's not just all about making the machine better. It's about making this combination of the human and machine work together better. So, how do humans work? Well, maybe psychology is a part of that. So maybe we care about, the scientific study of the human mind and how it functions, how people relate to the machine in front of them, how efficient they are in using this thing over long periods of time. But certainly we're not psychological engineers. So it seems like that's not quite it. Okay, social psychology. Well, there's a lot of those people together in that factory. They're working together, they're working with the machines, they're working with each other. There's a complex system of these people together. Well, Psych 101 tells us there's not just your standard psychology, there's social psychology. It's about these interactions. That certainly is interesting. We feel like we can use that as engineers, but it just doesn't feel like all we do. Because you zoom out a little bit farther and you see lots of other things in these complex systems that go beyond the human mind. So now you got humans, you got infrastructure, you got all sorts of decisions, you got laws, you got ethics. All of that gets thrown into there. And somebody says, I need a better intersection. Well, how do you build a better intersection? What is the science behind an intersection? And it is the intersection of sciences, perhaps, but there's something qualitatively different about the way things are coming together here and the way, photosynthesis works and so on and so forth. So really, when you think about it, industrial engineers are not only consuming knowledge, but they themselves are building knowledge as well, because the knowledge just doesn't exist. There is no one in the science side of this campus that is studying this system. I mean, there might be a few that they kind of do it on the side, but it is not their bread and butter. It is not what they do all the time. And so when someone drops us in the middle of a new system, which no one has ever optimized before, it's not a simple math problem. It's not like somebody hands you a formula and you just take the partial derivative and set it equal to 0 and leaves. You have to figure out, how does this system work before you can do any of the hard things it is to make the system work better. So with that in mind, it is my claim that we industrial engineers are the only engineers that have to straddle both science and engineering. We have to adopt the methods of the scientists in order to build knowledge, because no one else is going to do it for us. So, so over on science, design experiments, develop new models. That's going to be a major topic today. Make inferences about the validity of models. We are going to do that. So you walk into one of these manufacturing systems, and before you can do anything, you need a model of how the manufacturing system works. So you have to build that model. And as you're building that model, then somebody's going to ask you, how do you trust this model? How can you say that this model is a representation of what we're trying to optimize? And you have to validate that. So you have to make these inferences about the validity of your models, the same way the physicists do, the same way the chemists do, and so on and so forth. We have to do that too. Once we have those models, then we can go back to the good old-fashioned kind of easier process of engineering. So I think there's an irony here, is that when you hear the name industrial engineering, it sounds like it's the most removed from science, the most removed from nature. It is, industrial. Operations research doesn't even sound like engineering or science. It's business. It seems like it's way out there. But the irony is that the circle is closed at industrial engineering. We have to be our own scientists. We depend on science, but we depend on interactions among sciences, which no scientist cares about. No scientist is sort of being paid to investigate. So we're going to use statistics like scientists do. An electrical engineer, they maybe have to take a stats class because somebody made them. But you ask somebody 3 years out from getting their bachelor's in electrical engineering what a t-test is, and I'm guessing they're not going to be able to tell you what a t-test is used for. They're not going to tell you the difference between a t-test and an ANOVA and a chi-squared test. For all they know, a chi-squared test and a t-test are interchangeable tests. Right now, you might be feeling the same way. But at the end of this class, hopefully you will find those are important parts of your vocabulary that are as important to your vocabulary as they are to the scientists a couple rooms down, because you are the scientists of engineering. And that's what we're going to really work with throughout this semester. All right, any questions about that basic idea that we have to straddle both of these worlds? Okay. Now, the big words I have highlighted here is models. And so this class is very much about models. So that brings up the question, what are models? And so when we talk about models, this is, I think, the first thing that comes to a lot of people's minds, fashion models. And it is my claim that these are models in the same sense of the models that we care about in this class. So why are these fashion models in the class of models? What makes them models? How is that term being used here? What is the purpose of that term? What do you think? Yeah. What do they showcase? The clothing. So the idea here, so you're saying they're showcasing the clothing. So the clothing on a hanger is just a piece of fabric. But once you put it on a set of human shoulders, it starts giving you an idea of why is it useful to have the clothing on a set of human shoulders instead of on a chair or a hanger? An example, it gives you an idea of what it might look like, say, on your shoulders or on your body, right? So it is a representation of what it might look like on you. All right, so that's kind of an intricate answers a what if question. What if I put this on? Now, the interesting thing about fashion models are the degrees of freedom left over. So you look at this, you're supposed to just be looking at the clothes, right? But do you only look at the clothes? It's my guess that you might also evaluate the people wearing those clothes. And that might end up giving you some spillover in how you interpret the clothes. I mean, like this particular, this guy here, I might like the way this jacket looks on him, but I would probably have to lose half my body weight to look like him. I would have to, apparently both of these ones, I'd have to bend over like this. Like apparently that is a thing among these two random models, that they have that bend to them. They're wearing other things, like this might be showcasing the jacket, but he's got the glasses on. He's got more product in his hair than I wear in an entire week. These are other degrees of freedom which can be used to change how the model looks. And this will apply to our computational models as well. And here, my claim is they're deliberately trying to make these clothes look a particular way that they view that their demographic will find appealing, that goes beyond the properties of the clothes. But when we build simulation models, as we'll get to, then we will accidentally do this. We will accidentally put, the hair product in the model, not realizing that we're juicing up the model to look better. And we have to be very, very careful not to do that. So I will frequently use these images throughout the rest of the semester as a cautionary tale of when have you made an assumption that will make your results look better, but is not actually valid. Here, if we assume every person looks the way these two people do, then we can make some assumptions about how clothes will look on every person. But people don't look. If I look across this class, people look very different than these two people. And there's nothing wrong with that, but that suggests that if we want good models, good fashion models that are representative, then perhaps we should make different assumptions about how they look when we choose them. Likewise, if we want good computer models that are representative, we're going to have to make a different set of assumptions about the degrees of freedom we are free to play with when we build a computer model. Okay, so why is this? So my biological colleagues would call this an animal model. Like, so literally the mouse in the hand, if it was in a laboratory somewhere as part of an experiment, the mouse itself would be called an animal model. Why? How is model being used here? Why is this an animal model? Why is this a model? Thoughts? Why do we call it a model? I can wait. Yeah. So it could be that, so you're saying that maybe they're doing a study on mice. And so they want to see how mice behave or how certain things affect mice. Then you can get a mouse. And if you have enough of them, then maybe whatever patterns you see with them might generalize to the broader population of mice. What's another way you can use animals like this in a laboratory as models? Yeah. So then there might be a pharmaceutical model, for example. So it may be that mice and humans both have a particular disease that we've identified as having similar causes. And you might have a new drug that you think treats that disease. One approach before testing on humans might be to test on an animal that you claim is similar enough to a human so that the results that come out of the model are insightful, thinking about whether you should move on to testing on humans. Now, this is a mammal for sure, but it's a rodent. Humans don't have to grind down their teeth periodically to keep them from overgrowing. Humans don't have long tails. Humans have hair, but certainly not this much hair. This is not a perfect representation of a human, but it's probably closer than an ant, probably closer than a slug. So the thought here is that this can also answer a what if question. What if I gave this particular drug? Do we see a decline in symptoms of this particular disease that we know that the mouse has? And if we do, that gives us an idea that maybe we should keep moving forward with developing this drug for eventual human use. So that's another idea where this is helping to answer a what if question. What if the population, or what if a totally different species? Other models. This here is the Bohr model of an atom, very appropriate for a hall like this one. A lot of people don't realize this, but Bohr, when after he came up with this, noticed that this model helped him predict the properties of matter. So there were some things that would happen when you put matter together in certain ways in the laboratory that were unexplainable until you had this Bohr model of the atom that helped explain that when you shine light on things and so on and so forth, then there's certain things that happened that are predicted by this model. And because they match, then it suggests that this has explanatory ability. It helps you answer a what if question. If you can validate this is a good model, then you can start doing hypothetical experiments to the model that prevent you from having to actually do the experiment in the lab, at least not initially, similar to the animal model. But Bohr noticed that sometimes this model would not make good predictions. So Bohr thought, this is sort of like a circular solar system here, a sun and these playing circular orbits. Bohr knew that in our solar system, they actually follow elliptical orbits. So Bohr developed an elliptical model of the atom as well, where the orbits of the electrons followed these ellipses, and they made slightly different predictions, some that helped explain the deviations in the predictions from real world experiments that he was seeing with this model. But then, later, decades later, people come up with MO bond theory, stuff you learn in your first or second, college chemistry course. And these have the electrons that follow very, very different paths. They don't follow paths at all. They just exist in this probabilistic cloud. So as I go from this model to this model to this model, the electron seems to change. But this model was very good for a long time until someone suggested this model. And then this model seemed to have some strengths. And then this model came out. And then this model was much better at making predictions. So the electron is fundamentally changing as we move from one model to another to another. And then the physicists who study the nucleus come up with the standard model of particle physics here, where the electron is a sort of a totally different entity. So now up here, we have 4 different explanatory models that all do different things, that all have an electron. And then it starts making you wonder, what the hell is an electron? And the key thing here is that despite what you might have been told up until this point, an electron doesn't exist. But an electron is a useful concept. It is a concept which, it got us very far in doing physics and engineering up until this point. But for all you know, in 5, 10, 15 years, some enterprising graduate student a couple buildings over is going to come up with a totally new model for matter which doesn't have electrons in it. And it might make better predictions. And at that point, we just have to give up on the electron. I'm not saying that'll happen. It's very possible that all models of matter fundamentally will have electrons, or they'll have things that are electron-like. Maybe they'll be string-like instead of particles or whatever. But the point is here, it's not about the reality, it's about the utility. These models help us make sense of the world, but they do not need to be stances about what the world is. And that is going to be very important when we start building computer models, because your first instinct is going to say, I left something out. This does not feel like an airport because it doesn't have this little feature that I sometimes notice when I go to the airport. But then you have to ask yourself, how much would that little feature change your predictions of the model? And would adding that little feature in come with costs? And so sometimes leaving things out is actually better for the modeling process. So it's not about making things real, it's about making things useful. Okay, so another example of that, Newton versus Einstein. If after you learn about relativistic mechanics, then you start realizing that Newton had it all wrong. However, Newtonian mechanics is far more useful. When people build planes, they technically could design planes with relativistic mechanics, but things are so slow relative to the speed of light that it just use the broken model because it's not that broken. So really you have to ask yourself, how bad is my model? So, and oftentimes the additional utility you get out of your model compensates for the lack of realism. Because it has some realism. It works pretty well. So how well do you need it to work for your application? That is the key part of modeling. And that's going to be the key part of designing these computer models, is figuring out what to leave in and what to leave out. And most of the time, you can leave out all of this stuff, even though the physicists would tell you that fundamentally it's important. So that goes to this George Box quote. So you've probably seen this before. You probably have other professors have put this up. All models are wrong, but some are useful. George Box was a famous statistician. He was not knocking models here. So a lot of people misquote this and say that, oh, he was just one of these people saying, they're like, the Mark Twain quote about they're liars, they're damn liars, and they're statisticians. Like a lot of people would say that's what he's saying here. But no, he's actually telling you that no, this is a way he's instructing us on how to use models. So if you look at other stuff that Box says, other quotes from Box, the practical question is how wrong do they have to be to not be useful? So he's saying you got to accept that your model's wrong. You cannot go chasing after models that are right because you'll never get there. It's just chasing the horizon. But eventually you realize that you've got a good enough model, a model that suits your purposes, and you can stop there. Because really, the question you shouldn't be asking yourself, is do I have the whole truth? Because you're never going to have the whole truth. But is the model illuminating and useful? Newtonian mechanics is illuminating and useful. Figuring out, even though Newton assumed that gravity was constant everywhere, it was this GMM, over R squared, rule, that even Newton in his Principia, he said, I actually have no idea what's going on with gravity, but it seems to behave phenomenologically like this. So I'm going to leave this as an exercise for the reader to figure out gravity later. He said effectively that in his book, that there's going to drop this in. He recognized that that his model would suggest that if you suddenly obliterated the moon, that in an instant you would see the effect on the waves. And he said that just doesn't make sense. If you obliterated the sun, that immediately you would feel the effect. And he says, I know that doesn't make sense, but I don't have a better answer for it. So this is what I'm going to do. And you know what? He was right. His gravity works fine for everything that we do most of the time. Once you start, putting things in high speed orbit and low gravity, then maybe then we need to start looking for new models. But for stuff down here, that model works really well. So it's about, is it illuminating and useful? That's what we care about. So we're not trying to build perfect models. We're trying to build useful models. All right. So I found this fortune cookie once. I took a picture of it because I thought it was very much what we do in science and engineering, especially industrial engineering. Our goal is not to find the answer so much as to understand the question better. And that's what models, even imperfect models, do. All right, so what are models? As I've tried to hint at here, my definition of a model is, if I were to ask you this on a midterm, this is what I would be looking for. The simplest, most general definition of any type of model that's out there, and my claim is, give me anything that's labeled a model, I can frame it this way, is that models are anything that help provide us answers to what if questions. Leave that up there for a second. Okay. All right, and I would normally do an iClicker question here, but I'm out of practice, and so I'm going to hold off on that for the moment, just to make sure we're going to stay on time. Okay, so, and I normally would ask, what is the question that models answer? And then you would hopefully write in, what if? So that's what I want you to burn into your heads. Models answer what if questions. Okay, so types of models. So we're going to talk about different types of models in this class, but what are the total, what are all the different types of models? There can be statistical models. So statistical models, I would say, are these are models that are relationships that are inferred from data. That's where the statistical comes from here. So this red line, this regression line, it is a relationship between high school GPA and university GPA. You look at this data and you fit the line to it. And what this does, it helps you predict. If you know that someone in the future who's not in this data set, if they had roughly a high school GPA of 3.5, this relationship would say that their university GPA should be roughly 3.5. It helps answer a what if question. So what if you took someone in and they had this high school GPA, what would we predict their university GPA? So statistical models, they're relationships based on data, based on history. We can have graphical models, which are not necessarily based on data, but they're communicating an idea. They're communicating a hypothesis. So over here, this is communicating this idea that as your exercise intensity increases, your oxygen consumption should increase up to a point, which they call VO2 max. And at that point, your body starts, ceases to be able to increase its oxygen consumption and has to start metabolizing in a different way. And so the oxygen consumption, it flattens out here. And I thought it's cute that the person who put together this model actually put little fake data points here. So they're really saying, they're saying the what if here. If you were to measure these data, we would expect the data to fall along this line. That's why they put the little dots there. But really, they're just trying to communicate this idea that there's a knee in exercise intensity and oxygen consumption. So that is it's a graphical model. So you're just drawing out what you think is going to be there. Likewise, if I had a predator-prey population here with like wolves and rabbits, I might say, hypothetically speaking, there might be conditions in which I get these boom and bust cycles between predator and prey, where when you get lots of rabbits, then you're going to get a massive growth rate in wolves, but that's going to kill all the rabbits, which then will kill all the wolves because they won't have anything to eat. But then once there aren't any wolves around, the rabbits will rebound, and et cetera, et cetera. That's not based on data. That is communicating a model of what someone is proposing. It's what if. So what predictions would you make under this model? Well, I would predict that if you see a decline in wolves, you should see a rise in rabbits, and you should see that over and over again. And this is communicating that graphically. So we have graphical models. We also have laboratory models. We talked about the mouse as an animal model. You can have a human in a respirometry setup here. And then, there are interesting questions here about who is the system, or what is the system that human is representing. That could be a human brought in for a laboratory study on all humans, or that could be a human who went to their medical doctor and voiced an issue, and they are now testing themselves. So they're actually modeling themselves generically. Like they might say, whenever I walk between classes, I get really dizzy. Well, in the doctor's office, they can't see you when you're walking between classes. So they might put you up on this treadmill and see if they can get you to be dizzy here. Now, if you don't get dizzy in the doctor's office, that doesn't mean you don't get dizzy. So this in itself is a model of trying to represent the normal case that you came in about. But in order to do that representation, they need to build, a model, that a what if question. What if we exerted you in this particular way? If we think that it's exertion that's causing this, then I'm going to, use you on this treadmill as a model for you walking between classes, so that we can study that. So you can have objects that are modeling themselves at another time, for sure. At an airport, you can study the airport at one time to see, because that's all you have access to, and use that as a model of it at all times. Other models in the wild, other than just going to an airport. This is a real intersection. This is a snapshot from above a real intersection that has no traffic lights. So this is in a part of the world where they decided to engineer these busy streets without traffic lights. Now, based on your mental model, if I pose that what if question to you, you might have a mental model that would say, well, that would be mass chaos, there'd be collisions, et cetera. Just imagine if they got rid of the traffic lights at Millen University or something like that, and it would be, be terrible. But then you see this, and you see that although this isn't necessarily the cleanest solution, there's this sort of emergent eddy of traffic where traffic is flowing. Pedestrians are even moving through this mess. And so it's working in some sense of the word. It may not be the most efficient, but it certainly challenges maybe the mental model that I had. And now that I see this, I might update my mental model, and I use this as a model for what possibly could happen if the right conditions were there. in certain parts, if you have certain culture, maybe large intersections. I mean, there might be a lot of things that need to happen, but this at least gives me a model of, there is a world in which this can happen. This helps me answer a different sort of what if question. Now, we have to be careful, about how generalizable this is, because those assumptions won't be met everywhere. We also have to be careful about using models in the wild, because the people that are involved in that, as engineers, and this goes for even the electrical engineers, the chemical engineers, everything. We don't say it explicitly, but every time we release a product into the world, we're doing an experiment. We're gathering data, and when our constructions break in catastrophic ways, Titanic level ways, it's a tragedy. It is also an inevitable opportunity to learn, and people will learn. And it is not the way that you want to depend upon to gain your knowledge, but you will gain knowledge. When the Titanic sank, they learned a lot about the metallurgy of how brittle certain metals get in cold waters, to the point where if they bump even a small obstacle, they can shatter like an egg. So it doesn't have to be a giant iceberg that takes down a boat like this. A boat with the right, built out of the right or the wrong metals, that work so well in their normal waters, just pushing things out of the way, now crumbles in the colder waters. So a lot was learned here, but a lot was lost as well. So we try to build artificial models so that we don't have to do our learning in the field. This has been turned on its head in AI, in the world of AI. Now you have self-driving cars. You have a bunch of actual electronic applications, from your phone to your car and everything else, where they're learning a lot about you, and you're actually beta testing because there's on you. So, I mean, I remember back in the 80s, Microsoft and so on would you could join groups where you could beta test their software, but it wouldn't actually be released until it was a final version, and they weren't planning on gaining any information back from them. But now they've realized that most of their software is deployed in non-mission critical applications, and so they can release it quicker, and it's more competitive that way, and they'll just wait for things to break and then learn about how things break as they go. Sometimes, as it is, whatever's last summer, when we learned, as blue screens all over airports all over the world, went up, and planes had to be grounded as they were waiting for their software systems. Sometimes what they thought wasn't mission critical turns out it actually is. But still, most of the time, there's much more tolerance for that. So there's a lot more experimentation being going on real world systems. But whenever we can, if we do have a complex system that we can build inside a computer model and we can learn a lot from, that is highly preferable than waiting for the worst case scenario in the real world system. Now, here's an interesting thing, though. Going back to the George Box quote, all models are wrong, but some are useful. This idea that the models that we build may not have to be hyper realistic in order to be useful. And in fact, they might actually be more generalizable if they aren't quite as realistic. So I go back to that airport example. There might be some feature of an airport that you remember as being noticeable to you when you walked through the Phoenix Sky Harbor Airport. But if you think about it, if you start getting experience with other airports, that feature doesn't exist. If you say the only way I can do operations research on an airport is by incorporating that Sky Harbor specific feature, you might have built a model that tells you that makes it's much more precise predictions about Sky Harbor, but it suddenly makes it less realistic for every other airport. So if you're trying to talk about general airport operations, actually reducing realism can increase generalizability. So sometimes we build imperfect models, not just because it's hard to build perfect models. Sometimes imperfect models are actually better because they're more generalizable. And that's something that I hope we'll see more and more as we go through this. And so this general picture of, so Monopoly can be viewed, the board game Monopoly can be viewed as a overly simplistic model of how real estate works in a big city. It's, on one hand, you could say, I can't learn about real estate by playing Monopoly. But on the other hand, a little kid knows nothing about real estate. But after you teach them a little bit about Monopoly, once they can play Monopoly, you can start having conversations with them about real estate things. It's actually better than nothing. So somehow it captures the salient features of a real world model and it boils them down to focus on them so that you can have conversations about them, so you can explore issues that just revolve around the real estate. So then from there, you can get useful insight and understanding action in a real world system that isn't where then you might start layering on all of the other system level effects. But if you're focusing on just the real estate market, I mean, as an example, there is a jail in Monopoly that has no police. And so it's important to know that you can break the law and there are going to be consequences for that. But you don't have to model a whole full police force when you're talking about this. Like, how long does it take for you to get caught, et cetera, et cetera. All that stuff doesn't really matter to the high level decision making. And so, so you can get useful insight by only considering the salient features. And what's great about it is if you do have a simple model like this one, it makes it easier to communicate with people because now it becomes this boundary object that everyone can touch on. So you can say, you may not understand New York real estate, but do you understand Monopoly? Okay, yeah, I do. I get Monopoly. Now you can start using that as a common language. Or in the case of a computer-based model, you may say, you may not understand all this jargon I have about negative Jacobians and all the, some sort of, other sort of sophisticated calculus sounding words. But let me show you an example. And then you show them a computer simulation with and without a particular effect. And that then makes it much clearer to communicate. And so simplistic models can somehow sometimes make it easier to communicate with others, more so than the real system. All right, but we have to be careful. And so I'm gonna, again, these two fashion models will come up as my cautionary tale over the course of the semester. Whenever you make a model, you make assumptions about that model. Monopoly is not every real estate system. So there are certain assumptions about what goes on in Monopoly, which will make certain real estate maneuvers potentially more or less attractive in Monopoly. But in a real estate market, it'll be a totally different story. So, just like with the fashion here, there's some aspects of putting a jacket on a real person or a dress on a real person that are captured very well by these two fashion models. But there are other aspects of these fashion models that are confusing things and distracting things and are not generalizable. Okay. All right. So any questions about that before we do a couple more exercises? All right, so I mentioned mental models. I mentioned that your own brain is doing what if questions, and that means your own brain has got models inside it, these mental models. So what do you see? So I just put this image up here, and does anyone have a guess, or not a guess, but just a reaction? What do you see when you look at this set of images? Yeah, in the back? So I heard Star of David. So I guess that's because you sort of are tracing around the edge here and you see this six-pointed star. Any other thoughts when you look at this? Yeah. Triangle and circle. So maybe here's a triangle and here's a triangle. And maybe there's these three circles. Kind of okay. Other thoughts? And this is important, by the way, as you think about this, because before we can build models, we have to understand our assumptions in our own head to figure out what we want to encode in the computer models and what we want to leave out. So any other thoughts about this? Yeah. Pac-Man. So cartoon character here. I had a student, I think in this class, look at this once, and she went even farther than that and said, I see three Pac-Men that are going into a covered room to collectively find a ghost that they've been hunting for. Like she had a whole narrative about it that was inspired by this. And maybe now that I've said that narrative, now you have that in your head too. Any other thoughts about this? Now, as you look at this, none of those things that were just said are actually up here, right? Go ahead. Well, I mean, that kind of gets to the point I was just making here. There's actually no triangle, right? There's a this is a black ink splotch and another one and three black, kinked line segments. But the way they're arranged, your brain starts running models for how this could possibly happen. What if scenarios? Like, well, what if I took a white triangle and put it on top of a black outline triangle with three circles around it? You realize you have these mental models in your head that help you make sense of the world, that help you associate causal forces with data, but those are based on a lot of assumptions that are in your head, your own history. It's pulling a lot of your own personal experience into it when none of that is actually written here on the board. Likewise, over here, if you look at this cartoon, I'm guessing that if a lot of you look at this, you see you have certain opinions about you. You might, for one, say this is a human, and this human maybe is not somebody you would be friends with, perhaps. And I would maybe challenge that and say, I would say that these are not the proportions of a human. This is not a picture of a human, but clearly it seems to represent a human in our minds. Um, I would say, if this is a human, how can we cast aspersions to this, against this human? We're just seeing a picture of them, but you can make judgments about this person. Underneath this person, you can see there's something going on underneath here. Um, how many people would say that a circle is being cut out from underneath this human? A lot of people say circle. This is not a circle, right? Um, it's it is much wider than it is tall. But in your head, you have this idea of perspective. This what if I look at a circle from a particular angle, it is going to look like an oval. Why do we think the circle is the right shape? From different perspectives, ovals also look like ovals. So there could actually be an oval that's being cut out from underneath them. But in our head, we think that when people are being sabotaged, circles are cut out underneath them. That's just something we assume. Um, and we assume that we don't actually see a saw moving here, but we assume that it's a saw that is being used to cut out from underneath the person. So there's a bunch of things assumptions that we make in order to make sense of these scratches, which are coming from our own background experience. So this is sort of famous. I think it's still in the Louvre. This painting here, where you've got these. It's up here. It says tandem convergent. The models for fiancés, for people just entering into a lifelong relationship with each other. And then down here, tandem divergent. It's like a tandem bike for a couple just before a divorce. And so I think the idea being communicated here is an idea that those of us who've ever been in love or moving out of love will probably understand. At some points in the relationship, all you want to do is to be closer to that person, and you can't because it is physically impossible. And at other points, all you want to do is to get away from a person, but you can't because you are coupled to them. And that's sort of what's being communicated in this. And this is not reality. This is not saying anything. There's nothing about relationships that is explicit here, and yet we understand. We also, from a physical perspective, so someone's actually built these bikes. So here's an example down here where they've built that one. I don't need to build the bike, and it's not just because I'm a clever engineer. I think the average person out there who's not in a technical field does not have to build this bike to know that it is not a functioning bike. And that also goes to certain mental models we have about how the physical world works. We can say, what if you built that bike? And in our head, we can play forward, what would possibly happen. And we know that that bike would not be movable. So our mental models are doing a whole lot of work when we're looking at things like this. And so last example of this, so got a boat, there's it's the guy at the back of the boat steering the boat. And so if this is the first time they've ever been on a boat, if they want to turn left, they might push the rudder the wrong way. And the boat will turn right, because their mental model of the world was that when you're in a moving vehicle, what if you turn a steering device left? Well, if your mental model is that the device then turns left, then you should think that if I want to move the boat left, I'll push the rudder left. But they'll very quickly learn that it's reversed in this boat due to how the steering mechanism works, and they'll have to update that mental model. So they've got a mental model, and that mental model can change over time. Experience can build. That's the beauty of our mental models, is that they leverage a lot of experience and they can change over time. And that's good. But it can be bad too. So this is sort of a famous example people use in modeling courses. So pardon me, it's getting a little outdated, but that's sort of the point of it. A man and his son are driving in a car one day when they get into a fatal accident. The man is killed instantly. The boy is knocked unconscious, but he is still alive. He is rushed to the hospital and is needed of immediate surgery. The doctor enters the emergency room, looks at the boy and says, I can't operate on this boy. He is my son. So older audiences often cannot make sense of this scenario. But younger audiences traditionally can make sense of this scenario. So let's see what's going on here. So what explains the narrative here? A doctor could be a woman. Are there other explanations, other hypothetical explanations? Well, I said, and his son, a man and his son. Yeah. Adopted. Well, I mean, so I guess the idea here is a man and his son. And then, so we're saying that the man, oh, I see what you're saying. They're driving. I see. Yeah, that's a new explanation here. That's an interesting point, that the man could have been driving to the ER and his son is in a different car. That's true. Yeah, that's another way that possibly could be interpreted. Any other interpretations? The doctor could be male and could be, the son could have two fathers. So these are all explanations that in the complex world that we live in now make total sense. But to certain audiences above a particular age, their mental experience of the medical profession is that of all men and all, at least outwardly, heterosexual men. And so in that particular case, then older audiences read this and think it's a paradox, but younger audiences do not. Both of them mental models are at play, but there's different life experience contributes to each one. And that makes the mental models of the older audiences less useful as the world changes. So that's something we have to keep in mind. All models are wrong, or some are useful. This older audience's heuristics, their models in their heads, may not may have been useful at one particular time, but as the medical profession changed, as culture changed, then those old models that helped them answer what if questions stopped being useful. So, then how useful was your mental model here? A lot of, very quickly, we got answers. It's interesting to me, I've been teaching classes like this for many years, and I notice patterns. So there would be years or semesters where immediately I would get people saying the doctor is a woman. And then I would transition to semesters where somebody would like meet, and then I would wait, and then eventually I would get the doctor is gay. And then then I go other spans of time where those two, over several semesters in a row would flip. So it's sort of interesting, the experience that everyone shares is so dynamic. Like it can be shared among a cohort, but so different between cohorts. And that becomes, it sort of becomes dangerous to depend on mental models because you don't know what assumptions are being made by the other person. And that's why it's so nice to have simplistic models because we can all agree on that model. We can use that model as an object for conversation. So mental models, major strength, tremendous store of information, weakness, unreliable handling complexity and dynamic change. And they're also difficult to communicate to someone else. So what do we do when we want to leverage that experience, but we want to boil it down into things where we can all agree on the assumptions. And so we build quantitative models. And so what are quantitative models? So our major strengths in quantitative models here is that they're going to be better at handling dynamic change. So they're less static, whatever the assumptions are, as the assumptions change, then the models can change with them. They're better at handling these dynamic change. They're easier to communicate with others. They're on paper. The downside is they may incorporate very little information about the systems being modeled. So they may be overly simplistic. The types of quantitative models, we're going to focus on three types. The first type, mathematical modeling. This is the same sort of stuff that you'll see in 470. How many people are taking 470 or have taken 470? So your queuing models, a lot of those are mathematical models. They're approximations of queuing systems using mathematical theory. And once they're in the math, you can then derive solutions from that math. So this is a mathematical model of disease spread. We're not going to go into all the details of this so-called SIR model. The thing about this, this is basically, these are three derivatives coupled. It's a differential equation. When you have a model like this, it theoretically can provide exact solutions, but sometimes it's limited as to what context in which those solutions exist. So in this particular case here, you can get limiting solutions. And a lot of the stuff in 470 will also be limiting solutions. We'll say, what is the equilibrium queue length? So it doesn't tell you what the queue length is immediately after you open the doors to the restaurant, or what the queue length is a few seconds later or a few seconds later. But after things come to equilibrium, then it'll say based on the average speed that someone is to fill the order and the average encounter rate of people coming in, we would expect to see on average 5 people waiting in line. And so that exists in the limit. It exists at equilibrium, but it doesn't tell you about all of the transient times. So the math is great that it can make those it can predict 5, exactly 5. On average, it'll oscillate around 5. It doesn't tell you how big those oscillations will be, though. So there are limitations there. Tremendous advantages, but limitations. So to try to get around that, then we use so-called numerical models. You can take the same processes that you talk about in 470, but you can kind of express them as what happens from instant to instant. So at one instant, somebody comes in the door, the next instant, somebody leaves. And if you make assumptions about how quickly those things happen over time, then you can say, well, if roughly speaking, 5 people arrive every hour, then if I divide that by 60, then that's the fraction of someone that comes in every second. And whatever that means, a fraction of someone coming in. And you can build these kind of spreadsheet models that try to give you an idea of what the trajectory looks like over time so that things will settle out at the 470 solution, the 5 people waiting in line, but it gives you some idea of what things will look like. Well, it might go up to 30 people waiting in line at some points, and sometimes it's nobody, but then it averages out at like 5. This is so-called a numerical approximation. So it's a way of taking those differential equations, and because we can't solve them on paper, we solve them numerically, and that becomes this numerical approximation that does not provide us exact answers. It just provides us these graphs. And that's a little better in some ways, but we've lost something in other ways. It also becomes very difficult for us to change these expressions up top here, because now we have to update this entire spreadsheet. So that's when we get to the type of models we talk about in this class, simulation models, where these models have been trying to be built so that we try to capture the salient features of the model in a way that is easy to update later. So if you want to add in new things later or take things away, we'll have a very quick way of doing that. Behind the scenes, the computational tool effectively builds one of those ugly spreadsheets for you. So it takes that out of your hands. So you just have to specify the constraints about what goes into that spreadsheet and it builds it for you. And then it simulates it for you and it gives you those graphs out. So we'll find that this is going to be fast. We can model dynamical behavior. It's very flexible. We can change them easily, and we can integrate lots and lots of complex, unrelated disciplines. And they're a good communication tool because we can show people graphs, but we can also display the models in a way that isn't, mathematical. It's at a higher level. The downside is approximate solutions. And because we're going to depend upon software tools, we're depending upon the developers of those software tools. And that will be something that we have to be very aware of the decisions that those developers made. So it's kind of very high level, but that's the sort of stuff that we're going to be working with in the class. Other, industries use these tools. So Southwest Airlines, they're moving away from open seating. They came up with the open seating idea by using simulation models because people thought for the 80s and early 90s that the only way you could board a plane efficiently was back to front, out to in. So they ran a bunch of simulation models with simulated people entering planes and found out it was all a wash. It doesn't matter how you board people. It basically doesn't change the boarding time that much. So they realized that they could just do open boarding and then they could monetize aspects of the boarding order. And then now that they're moving away from open seating, they're moving to sort of a purely monetized order. And that's kind of where all the other airlines, how they responded to that as well. So now, you don't board by where you are in the seat. I mean, that's the default is they'll say you can board by where you are. Like if you go to United, you always, I think, board windows first and then middle and then aisle. So if you want to sit in the aisle and you pick an aisle seat, if you don't pay for it, you're going to board last. So they're like, oh, but if you want to have an aisle seat and board early, you just pay more. And it has nothing to do with the operations. It's purely a way to make money. And that came out of modeling efficiency and figuring out that actually the boarding order doesn't matter. There's a bunch of other kind of examples of that too. For time, I'm going to kind of skip through them, but the point here is that you can model, complex, this was a model that came out of ASU where people talked about how boarding order changed the dynamics of infection risk. So different boarding orders may not affect how quickly people get on the plane, but they do affect how likely it is for disease to spread as people board the plane, which is, I guess, kind of interesting. So point that I'm kind of wrapping up here with is that we're going to combine mathematics, statistics, and programming in this class. I would say this class is far more about far more than just programming. We have to build models that are useful. They provide useful insights, but they also have to be useful to us. And so we need to be able to run them in efficient time. And so we have to figure out how to make them fast models as well. And to do both of these things, we have to use good statistical methods. We cram all of this inside I-475. It's largely a survey. If any of these things become really exciting to you, you can go, we have courses at graduate level courses that expand all three of these. And so you can go much deeper in this. All right, so any questions? If not, these are our reminders. So A2, don't forget, it's out there and due by Thursday. Lab 1 stuff, other stuff is available online. And I'll let you guys get out of here, so don't worry about a clicker today, but there will be a clicker on Thursday. Let me shut off here first.